Okay, we are now going to talk more about the distribution of x bar. And we're going to talk about something called the central limit theorem as well. I'm going to split this up into 3 shorter videos, and then we'll have a 4th video where we're going to do some more examples that involve doing problems and kind of taking into account what the central limit theorem says. So we're going to start out with a definition of what the book calls the sampling distribution of the sample means. And as we'll see in a minute, this is the same as the distribution of x bar. Okay, so the sampling distribution of the sample means is basically the distribution of all the possible samples, or all the possible sample means for samples of a given size that can be obtained from a population. And there's a lot there to wrap your mind around, and I'm going to help you do it. But first, let me show you the connection between this and the distribution of x bar. So this is the technical name for d of x bar, or distribution of x bar. And so basically what I've done here is sampling distribution of the sample means. That's the technical name. And I've just crossed out the sampling, because this is a mouthful here. So distribution of the sample means. So it's not so much to say I just don't worry about saying sampling distribution of the sample means, but just distribution of the sample means. But then I shorten it even more here. The sample means, the symbol for that is just x bar. So then I shorten it to distribution of x bar. And then when I have to write it over and over again, I shorten it again to just d of x bar. Okay? So this is the actual name, the sampling distribution of the sample means. And you can shorten it to distribution of the sample means, which would be distribution of x bar. And then I really shorten it by calling it d of x bar. Okay? So what is this here? The distribution of all the possible sample means for samples of a given size that can be obtained from a population. Okay? Well, let me give you an example just to help you wrap your mind around this. Okay? So let's say our population has, we'll just say 30 observations in it. Okay, so our population has n equals 30. That's a rather small population, of course. Usually populations are very large. And then let's take out samples. We'll say samples of size 5. Okay, so we'll say that the samples have n equals 5. So out of a population of 30, we're going to take out samples of size 5. So a rather small population, rather small sample, but even with this, there are a lot of possible samples you could draw. And in fact, we can use our calculators to calculate the number of possible samples. And we do that using the combination key. If you remember, NCR, or in this case 30, choose 5. Out of 30, choose 5. This tells us how many ways we can do that. And if you remember, this was a pretty large number. Out of 30, if we choose 5, there are 142,506 possible samples. Okay? So 142,506. Okay, so that is a lot of samples. You could probably never actually pull out every single one or list all the possible samples. Even with this small population and these small samples, there's too many to actually list them all out. Okay, it boggles the mind. So if your population had 1 million people and you took out samples of size 500, there would literally be more possible samples than there are atoms in the entire universe. And that's not an exaggeration. There would be much, much more. So these numbers get very, very large. Okay? So let's say, though, we actually did this and we pulled out all these possible sample means. And we took out the first sample, calculated the mean, the second one, the third one, fourth one, fifth one, sixth one, and we just kept doing this, right? And we just kept doing it until we got to the last one. So then we have a huge data set, and they would be all the sample means, right? And how many of these would there be? There are 142,506 sample means. Crazy sample means. Okay, so there's a lot of them. So let's say I had this data set and I actually organized it here. So we have sample means, so we're making a frequency distribution. Okay, and so we actually put in, you know, from here to here, from here to here. Sample means from here to here. So we have these, you know, these intervals here, and then we have the frequency for how many sample means lie in each interval. So we had values here for each of these. Okay, and these frequencies would be in the thousands. Okay, and what we would be doing is we'd be making a frequency distribution table for all these sample means. And then we could make a histogram. And the histogram, these would be sample means down here. And this would be the frequency. This would be number of samples, right? This would be the actual value of the sample means. These would be the number of samples that have that many means. And we would have a distribution. And what ends up happening, we're going to find out, and this is actually what the central limit theorem says, is that this distribution is going to be either normal or approximately normal, given that our samples are sufficiently large. And we're going to look at that in another video. But the thing is, this video, or this distribution of all these possible sample means, is going to be the distribution is going to be normal or approximately normal. So this would be d of x bar. This would be the distribution of x bar for samples of size 5. Okay, and then what we learned before is that the mean of this distribution is equal to the mean of the population, and the standard deviation of the distribution is equal to the standard deviation of the population divided by the square root of n. Okay, and so what is this mean? This mu with the little x bar subscript? It would be adding all of these together and then dividing by 142,506. It'd be taking the mean of this data set. So it'd be the mean of all these sample means. And that's going to equal the mean of the population. So they have proven that. They proved that algebraically. And then if you took the standard deviation of all these means, you would get this, and it would be equal to the standard deviation of the population over the square root of n. And this here would be your d of x bar. This would be the sampling distribution of the sample means for samples of size 5. Okay, so that's our first video where I'm just describing what d of x bar is. And as you can see, it's conceptually it's pretty deep, because the number of possible samples you can draw out is very, very large and hard to wrap your mind around. But this is what it is. It is how all those possible sample means, how they are distributed. So in the next video, we're going to learn a little more about the mean and standard deviation of the distribution of X bar.